yeah, so how to apply the uh, somehow picture of the generators to second generators to the control loop of the power converters. So the idea is coming from this hypothesis that it is possible to develop a new synchronous generator based on power electronics, which instead of iron and copper, we have actually this type of power converters. It has the benefit of the conventional associated to conventional power generator. So what we discussed on Friday, if I'm not wrong, so we said that we up to here we know that how we can use the PI controller, and based on that make the control, current control, and inject the power based on our demand. But here mentioned that instead of having the impedance, we can create the virtual admittance. And the reason is that when we use the admittance, in fact, here, so this one is working as a first order low pass filter. Instead of increasing the distortion, high frequency distortion, it reduces, or it works like a filter for the removing this distortion injected to the grid. So now we see that we have the actually virtual admittance, and we have also voltage of the point of common coupling, so it's coming from here. And we have also this voltage that coming from the generator. So we need to consider the electromechanical model of the synchronous generator. Up to here is clear? So get back to, yeah. Which one? We reference here, you mean? Okay. This one, why we don't get somewhere else? So if I get here, okay, yes. This is the load. No, this is load. Load, yeah. This is a load voltage, okay? Voltage of point of common coupling, which is over the grid side or load side. Okay? So, we said that in active power delivered from the synchronous generator to the grid can be calculated by EV over X sine delta. So normally the value of the E and V are close to each other to rated value. So for this, the load angle is not big. So instead of sine delta, we can put delta. So for example, if degree is 1 degree, delta is 1 degree, then is like instead of sine 1, we put P over 180. So for this case, we can simply consider the electric power injected to the grid from synchronous generator is EV over X delta. And in conventional generator, we have actually two parts, mechanical part, and which is provided by prime mover, and also we have actually electric part is the output power. So you mentioned P in and PS, or we can say anything. So by this, we deliver the power to the grid. So when we provide this mechanical power, which rotate the synchron shaft, so it is in the omega S. So it is not equal to the value of this we need, but basically this omega S somehow we need to provide the acceleration torque, which is calculated by P mechanical minus P electrical over the omega. So this is the acceleration torque. So this torque gives the actually rotor an angle acceleration which can be calculated by J times, so acceleration is coming from the force and force coming from the provision of the kinetic energy. Okay, so by this acceleration angle can be actually somehow provided this torque. So the J times 2 acceleration angle is providing this torque. So this is the definition of the actually the structure of the synchronous generator. So by this we have the alpha, which is the acceleration. So we can put, instead of alpha, we can put it d omega to dt. And instead of d omega to dt, we can put d2 theta to dt. So this is the position, speed, acceleration. So the derivative of the position is the speed, and the derivative of the speed is acceleration. So by this, we can actually calculate this torque. So J is the moment of inertia that we have in rotor, and omega r is the angular speed for the rotor, and theta is the angular position. So this is why we create the angular position, which is not exactly equal to the angular of the instantaneous angle of the grid. So there are always some difference between the angular frequency of the, angle of the instantaneous angle of the grid, and also the angular position of the rotor. So now we get back this equation. Equation is not actually calculated, is somehow complicated, is somehow definition. Okay? So yes, because there are two different parts. So when you connect actually this rotor to the generator to the grid, then it doesn't mean that they are, because we don't have PLL to consider that one in the control loop of the converter. We had in converter, but for synchronous generator, we don't know the position of that, so we cannot fix based on that. So we start from the zero, and then in the point we see that there are some difference between that. The speed is, but they are in a nominal value, so they are somehow not too much different from each other. So if you are going to provide electricity for 400 volt grid, then the structure of the generator should be designed based on that. Okay? So then you're expecting something close to 400, not 200 or 1000. Okay? This is why we said that they are somehow close to each other. I mean, the difference between the angle of the synchronous generator and the grid is not too much. The delta is not very big. Definitely it should be the same, but it is not absolutely the same. So after the steady state, transient in the steady state, they become the same. Yeah. So, but we get back again to this. So we said that we have a P mechanical or input power minus P electrical as output power, and then we have omega S. So we get back here, we have P mechanical minus P electrical. Yeah? So P mechanical minus P electrical is delta P. So if we divide it by omega S, we have the torque. Is it clear enough? So is it clear? So P mechanical minus P electrical is delta P, okay? Then we have 1 over omega S which is coming from this equation, P mechanical minus P electrical, so is equal to torque. And if we divide the torque to J, torque over the J is alpha R. So alpha R, and if we take the integral of the alpha R, it will be omega R. So if we get back to this equation, we see that if we get the integral from the alpha R, we can reach to omega R. So we go to omega R. And if we get the integral from omega R, we have theta. So this is the position, this is the speed, and this is the acceleration. We get the integral, or we get the derivative. So now we have the angle of the rotor, and we need also to compare the angle with the grid to provide that difference and make the required action. So this is grid angle and this is the rotor angle. So if we get back in here, delta will be calculated by the difference between the rotor and grid angle. So if we get back to this equation, we have the delta by this. We calculated rotor angle and we have the grid angle. So the difference between these two angles is delta. So then we have also from this equation EV divided by X times to delta is P electrical. So P electrical can be calculated by delta times to EV over X. This is not something complicated, is it? Yeah. Now we know how to calculate the value of the electrical power based on the mechanical power. And if you see in any types of the controller, if we are going to make sure that the controller is working well, we should consider that the difference between the measured components with the reference value. So we see that, you know, if P mechanical minus P electrical have some problems, we have the delta P. And when the difference is higher, it means that we have too much losses. So for this, now this is the structure of the actually electromechanical model of the synchron generator. Now we should actually replace this part in the control loop of the converter. So what we need to modelize that one here. If we modelize that one here, in fact, our system is working like a synchron generator because we are creating that one based on the model of the synchron generator. Okay? So what we have here is for the synchron generator. Now we are going to emulate or impose this part in the control loop of the converter. So now we get back again to this equation. We see that we have P mechanical, P electrical. So P electrical is equal to P mechanical minus P electrical. P mechanical minus P electrical times to 1 over 2 omega S times to 1 over J times to 1 S times to 1 S times to V over X. Yeah? So by this assumption, what we have, this is the P max, so we can replace this one as a P max. And we have P electric equal to P mechanical minus P electrical times to 1 over omega S, 1 over J, 1 over S, 1 over S, P max. So if we calculate this equation, it means that P electrical is equal to P mechanical minus P electrical times to P max over to S2J omega. So by this, S2J omega transfer to the other side, S2J omega P electric is equal to P mechanical minus P electrical times to P max. Is it clear enough? It's just a mathematical equation. Doesn't matter you get it or not. The important theta, yeah, this one. We, yeah, for this one we don't consider that one actually. Yeah, yeah. Because we consider, I mean, we have a small signal and large signal. Something like fault is a large signal. Some swing, dynamic, this type of things related to the transient part of the any devices, and also consider of the yeah. You can, yeah, like this one is, I mean, load can be also little bit dynamic changes, or this should be, but depended, yeah. If we consider the load for the short time, then it can be considered a small signal. Yeah. Yes, if it is a small one, yeah. But when we are talking about like a short circuit in a system, then it could be. So, for example, if you are going to consider the fault right through capability of the converter-based generator, we don't go through the small signal analysis. We have actually different perspective. You cannot go to, okay, delta of I is this one, because we don't have delta I changes. We have a big changes. I mean, for example, in the circuit breaker 800 ampere we have, when short circuit happen, the short circuit current go to 60 K. It's like I don't know, 80 or 75 times more. So this is actually need the different analysis for a small signal. But for the dynamic changes, this transient operating condition, we consider the small signal analysis. So, any questions so far? No? Okay, good. So now we have actually this equation based on this model, electromechanical small signal model of the synchron generator, and the rate of the electric power to mechanical power is calculated by P max over to J omega S, S2 plus P max over to J omega S. So by this assumption, we have actually marginal stability, which the boundary is the natural frequency in this. Okay, so it means that, you know, if you pass the border, then system will be oscillating forever. So for this is actually our natural frequency can be calculated based on the model of the system. So up to here, we say actually now we have the somehow mathematical model of the synchron generator, which should be considered in the control loop of the converter, which somehow emulate the behavior of the synchron generator in the converter-based generator. This is why we call this converter-based generator as a virtual synchron generator, because it is not really synchron generator, but it behaves like a synchron generator. In synchron generator, we have actually a damper, but basically we use this damper for the damping the oscillation in the grid. But the problem is that due to some limitation, mechanical and electrical limitation, they are not working perfectly. So for this, we have actually some problem for the transient stability of the system, which when this type of things happening, the transient issue happening in the power grid, then it cannot damp it fastly or probably perfectly. So for this case, always they are fluctuating. So by this, we need to provide a solution, and the solution is the species, which consider actually some extra components and add some new feature in the control of the converter based, actually grid connected converter, or some other types of the converter topologies to solve this problem. So by this assumption, the comparison between the SPC and virtual and synchronous generator is that SPC can provide the functionality that synchronous generator somehow can provide, but the benefit of the SPC is that in SPC we can provide the better damping when the transient instability happening. So it has the some strengths of the synchronous generator, but it doesn't have the drawback of the synchronous generator. This is the positive point of the SPC comparison with the synchronous generator. So again, we get back to this. We see this is actually a small signal model of the synchronous generator. But what we are going to do in synchronous generator, in virtual synchronous generator, we will somehow develop it by adding adaptive power controller, which reduce the oscillation and provide the faster response to disturbances. So for this case, we add a PLC, and it is power loop controller. And by this, the idea for adding this type of PLC, which is the function that you can actually decide how much actually it is complicated or simple. So you can consider that, you know, it provide somehow frequency changes, estimate the frequency changes based on the power changes. So let's see how it works. So in synchronous generator, we had the input power and output power. Okay, so mechanical power converted to electric power. Okay, so based on that, what we are expecting is that, you know, we have a quiet, less losses, and it provides somehow a smooth power for the power grid. So the electric power that injected from the synchronous generator to the grid, and the difference between the mechanical power give the delta P. Okay, so these changes provide some, because we have changes in the active power. So it means that we have changes in frequency. Okay, so this PLC calculate this delta omega based on the delta P. So as much as delta P is bigger, delta omega should be smaller or bigger? Bigger. So the difference between the input and output power are more. In fact, what we actually have, it means that we have more fluctuation in the frequency, because active power impacts the frequency, reactive power impacts the voltage. So by this, we have the delta omega, which actually provide somehow is a link with the delta P. So this delta omega with the synchronous frequency provide the delta omega R, the frequency of the rotor. Okay, so by this provide, because, you know, you have rotor, it's actually rotating and provide the frequency. This frequency should be equal to frequency of the reference we need, can be grid frequency. So when it is not equal with that, it means that we have some problem, because we cannot synchronize that. Nice. So PLC detect how much difference appeared in the frequency between the omega r and omega s. So they calculate that omega and add with the omega s to create the omega r. So now we have the omega r is the frequency of the rotor. And if we get the integral of this one, we have the theta for the rotor. So it means that we have the actually angle of the rotor, and we have the angle of the grid, so we have the delta. So based on delta, we have the Pmax and output power. So it means that by this, we can calculate the exact power we need to synchronize our system with the grid and provide the active power for the power grid like a synchron generator. So by this assumption, we also consider that the PLC can be designed using various techniques. So what we consider in our course, we consider omega c over to s plus omega c. But you can consider different. It depended actually what you are looking for, but this is one of the most simplest one. And the complexity of the controller depends on the required system response for different applications. So if you need something, you should calculate it and see that this is my response that I need. So if you have a strong grid or you have the weak grid, the response time should be different. And if you have actually some stable network or some unreliable network, how you can compensate it, then it can be calculated the different PLC. And so as I mentioned, this is the most simplest one that we can consider for this model. Is it clear up to now? Did you get why we are going to reach to this model? What is the reason? So again, one time more to make sure all we are in the same stage. So we said that we had the controller, this converter, up to, before this chapter, in previous chapter, we calculate the delta I current controller and provide the active and reactive power and compensate the harmonic, this type of things. But then we said that if we are going to actually provide supportive functionality for the power grid by converter, we need to emulate the behavior of the synchron generator. And we said that the model with virtual admittance is good, and the reason is that we can actually use the admittance as a filter and filterize the injected current from the converter to the grid. And the model we have for the synchron generator should be emulated here. So we said that, in electric, actually synchron generator, P mechanical minus P electrical over to omega c is equal to the torque we provided. So this torque also provides actually angular frequency for the rotor, which this acceleration actually is the derivative of the speed, and derivative of the speed is also position or theta. So by this, we just replace in the model. So we said that we have the P mechanical and P electrical, and we have the delta P is the difference between the output or P electrical, electric power generated by generator, and also P mechanical is the input power we provide. So by this delta P can provide actually divided by omega c, provide the torque. And we also divided by inertia, it provides the alpha, which is the acceleration, and then we get the integral of the alpha, then we have the speed for the rotor, and also by integral of the speed of the rotor, we can reach the position of the rotor, which have the theta, so the delta can be difference between the omega r and omega c. So then we have E and B and X, so we can calculate the P electrical. Up to here, I think it's completely clear, but we mentioned that, for this model, we need to consider actually somehow some extra benefit comparison with the conventional synchronous generator. For this reason, we add a PLC which give the difference power between the reference power and measured power. So when we have this fluctuation, it gives to the PLC, and PLC calculate the value of the frequency changes. So these frequency changes, is we add these frequency changes with the omega S, we have the frequency of the rotor. So when we have the frequency of the rotor, again we proceed the same omega, theta, delta, E and E. So we can calculate the model we have for the synchronous generator in the control loop of the converter. So if we get back to the model we had, this model, now we can consider this part. And if with this part, we model, actually, we apply the model of the synchronous generator, in fact, this converter will be controlled based on the model of the synchronous generator. So for this case, we get back again to this equation, this model. So we see that we had input power minus output power is delta P. And after delta P, we consider this one, delta P, and then give the PLC. So we have the PLC. PLC provide the delta omega. Okay? So in this delta omega is linked with the difference between P in and P out. So based on delta omega, and omega S is the constant value, so we have the omega R. So now we have the omega R, we know what is the voltage of the reference, and we use the voltage control oscillator, which is providing actually the voltage we need to consider for the synchronous generator or the output of the converter. So by this, you know that the converter is going to be connected to the 400 volt grid. So you know that what is the value of the reference voltage. So by this, you can actually provide the three-phase system with 120 degrees for each phase. Is it clear? This is not something complicated. This is not probably calculation of the delta omega is a little bit challenging, but for this we just have the omega R and E. So based on that, we provide the reference value for the output voltage of the converter. So by this assumption, you have actually voltage and delta V, and then get back the reason that why we use the admittance and control the system. So what we have here is that we have the model, which we have the natural frequency considering this one, and based on that we know what is the border of the stability. We have actually frequency damping, so it provides the better damping in the model of the converter. It's better than the conventional generator. And also we have a function of the inertia is coming from here. Omega n is the function of the, so P max is the calculating, actually omega s is constant value, and the J is the value of the inertia that we can provide and keep the system in the stable operating condition. Is it clear? Okay. So now get back about the model that we developed here. We see that this model provided to somehow emulate the behavior of the synchronous generator. And the reason is that what we provided here is based on the operation of the synchronous generator. The benefit of this model is that it has the functionality which synchronous generator can provide for the grid, like a inertia and some other things. But the advantage of this technology compared to the conventional synchronous generator is that in this technology, we can provide the better damping, oscillation damping in comparison with the synchron generator, conventional synchron generator, and damp the system when we have the more oscillation. So now we get back again to this model. We see that we have P in minus P out is delta P. We have PLC. PLC is K times 2 omega C plus S plus omega C. So this is the model we considered in here, but later you can actually consider the different, but this is something easy we can consider. So we have this PLC, and then we have integral from here. So we have 1 over S times to P max, we have equal to PS. Okay? So by this assumption, if we get back to this calculation, we reach to PS to P in is equal to K omega C P max over to S to omega C S plus K omega C P max. Okay? So this is just a calculation of this transform function. So by this assumption, this is a second order equation that is equal to S to 2Q 2 omega Kc ns plus omega n2. So by just considering this equation, 2 Kc omega n is equal to omega c, and omega n power 2 is equal to K omega c P max. Okay, so omega n is equal to K omega c P max, and Kc is omega c 2 K. So by just replacing the omega n value, we can reach to this equation. So what is the Kc now? What is the value of Kc? Yeah, this one. So in conventional generator, we have the swing equation. So we have the J here, we can calculate it, but we have D delta omega. What is the D delta omega? D is damping factor, okay? So by the damping factor, so if our system is swing this one like this, or another one like this, so which one is better? This one or that one? That one, because it's not swing. And the reason is that we have a better damper to damp the swing. Okay? So for this case, in converter system, we have actually Kc is the damping factor. If you remember in previous chapter, we said that Kc is equal to 0.707 or a square root of 2 over 2. This is the optimal value. But here you can consider that, the operation of the system is dependent to the different things. So for this, we can design the Kc for the optimal operating condition, and omega n is also the natural frequency which provide the border for the stability. So again, we get back to the equation 11. This one, we see that we calculate the omega n, we have the P max and omega c. We can calculate the J. By this. This is the inertia can be injected from the converter to the grid. The error exactly when this discussion was finished. Yeah. So Now I don't know what should I say to them. Should I repeat again? Should I skip this part? So welcome. Do you have any excuse to explain the delay? Bad breakfast, slept, mosquitoes, something annoying us. Yeah? Okay, good. Siddhant? What is the kisi? What is the kisi? Exactly. Good. Yeah. So anyway, now we know that actually we can provide the inertia that we need to inject for to the grid, and also we know that what is the value of the damping factor. And do you have any idea about this equation? I mean, so we know that this J is calculated by this, but okay, how should we understand what is the value of the J? We have P max is calculated by V times to E over to X. So this is the constant. We have omega C, omega S, which is the frequency that we need, is a constant also. But this omega n, what is the meaning of omega n? Is the natural frequency. So what is the meaning of natural frequency? So natural frequency, if I'm not, yeah, here. This transfer function shows that our simplified synchron generator has the marginal stability with a steady oscillatory response at the natural frequency of this one. Okay? So when you analyze the stability of the system, you should consider that if we pass that border, then system will be unstable. So for this case, when you're calculating the value of the J, you should consider that what is the natural frequency, and then you calculate it, or you calculate the value of the inertia we need to keep the grid stable. So basically in simulation, it is not calculated because you cannot see that, what is the value of the omega n, or natural frequency. So for this case, most of the time, we provide the simulation first and see what is the value that the system frequency get the unstable, and then we replace this omega n in the equation and calculate the value of the inertia we need to inject from the converter to the grid. Yeah? Did you get the point? Yes or not, gentlemen? Okay. No, we have a border, okay? So this marginal value, marginal stability, okay? So it's coming from the natural frequency. So natural frequency means that swinging, continuously, okay? So it means that if we pass this border, the system will swing continuously and system will be unstable. So if we know that what is this border line, we will not exceed it. So by this we should know that what is the value for that one. When we make the simulation, we can see that if we exceed some value in the frequency, natural frequency, we see that it swings. So if we consider this one in the model of the system, we can see what is the value of the inertia we need to inject to keep this stable. Because when we make the simulation, we increase the inertia, we see that system is getting more stable. But when we pass some more, then system will be unstable. It means that we pass this omega n. Yeah. Any questions so far? Is it clear for you? Yes? Okay. Yes. Arya? What is the reason to using this virtual synchron generator? Why do we need to provide virtual synchron generator? So assuming you apply for a job in a company, and I'm person in the company, I'm going to take the interview actually from you. So in your CV, you mentioned that your work, actually you passed this certificate, I don't know what you call it, and in the control of the converter-based generator, yeah? So in converter-based generator, we need to emulate the behavior of the synchron generator in the control loop of the power converter to provide the functionality for the grid. Why? So you go, register another course, listen to the course, eat the food of the dormitory, not the street food. Okay, pay attention to everything, learn it, and return back. Okay? Okay. Or listen at least now. Okay, good. You want to have actually your to see that what you're thinking. He was absent about that person. I mean, again, one time again, I say, there was a king, had the son, and the son always was actually sitting or actually lying, look at the sky. Didn't eat something, didn't talk with anybody, and then the king become a little bit worried about that one and bring a very expert doctor, and doctor look at everything seems good, and then take the hand, give it to me like this, okay, this part, and said that Afghanistan, Pakistan, China, India, and then something changed more, okay? Then said that, okay, Delhi, Mumbai, Hyderabad, Warangal, said it's more, okay? Then I said that, okay, this street, that street, okay, then more, and then see that this red color, blue color, door, and white color, wow, okay, so said that, okay, your son is in love with the girl that the address is here, okay? So I should do the same with you because you look at me, but you don't actually, your mind is somewhere else, yeah? Yes. Okay, good. So, okay, one time again, just because this is very important. So then, we have this model. We discuss in the control of the converter with the PI, and we see that we can compensate the active-reactive harmonic, but we could not provide any inertia for the grid. And if we couldn't provide the inertia for the grid, then the problem for the stability happening in future grid, which is dominated fully by renewable energy sources, which are basically based on the renewable power electronic converter. So by this, we decided to modelize the behavior of the synchron generator and then add this part in the control loop of the converter. Then the control loop, the converter behave like a synchron generator. So for this, in synchron generator, we had actually torque, which is the difference between the power provided by mechanical part and electrical part, and over to omega. So we have also angular acceleration, which is the J times 2 to omega r. So by this, omega is this alpha is acceleration, then not omega r, alpha r. Acceleration. So if we take the derivative of the acceleration, no, we take, derivative of acceleration, we reach the, acceleration is the derivative of the speed, and speed is derivative of the position in the physics, okay? So by this, you can actually replace this one by this equation, okay? So now we get back here. We see that P mechanical minus P electrical. P mechanical means that we have something behind of the generator which turn the shaft of this rotor and provide the output electricity. Okay? So P mechanical minus P electrical is delta P. Okay? Divided by omega C is torque. So divided by omega C is torque. And torque divided by J is alpha. And if we get the integral of alpha is omega. If we take the integral of omega, we have theta. So in fact, we have the angle of the theta. So what we need is omega. So the difference between omega, what we need is the theta G, grid. So the difference between this is the delta, what we discussed in the beginning of the year. Okay? So delta times 2 E V over X is P electric. So we can calculate the electric power by this. Then we see that this is the generator model, and the problem of the synchronous generator is that benefit is that we can provide the inertia for the grid, but the problem is that it cannot provide the very good damping because of the limitation in electrical and mechanical limitation of the synchronous generator. So for this case, we use a PLC or power loop controller, and we give the power difference between the input and output of the system, and based on that, when we have the change in the power, in fact we have the change in the frequency. Am I right? So this frequency changes can be added by the reference frequency to provide the frequency of the rotor we need. And again, we go actually take the integral, we have the theta, compare the theta of the grid, we have delta, and we can calculate the PS or output power. So by this, we replace this as the electromechanical model of the synchronous generator in the control loop of the converter. And by this assumption, converter is working like a area, give me your hand. Yeah, you are clear, everybody knows that. Okay, what you are thinking. So it's thinking about synchronous generator. Okay, so it's working like a synchronous generator. Synchronous generator, okay? So in fact, we modelize the behavior of the synchronous generator in the control loop of the converter. So our converter is working as a synchronous generator. We call it virtual synchronous generator. So it has the benefit of the actually conventional synchronous generator, and it doesn't have the drawback of the conventional synchronous generator. What was the drawback of the conventional synchronous generator? It doesn't have a very good damping because of the limitation in what? In electrical and mechanical limitation of this type of generator. So this is what we had. This is the model. So based on this model, this transfer function, we can see that what is the value of the omega n. It means that the margin that our system will be stable or jump to instability. And also we can consider the Kc, which is the damping factor. It means that we can control it and have the best damping factor. When oscillation happening, we damp it. And also we can provide the inertia for the grid. So the value of the inertia and how much inertia is needed to provide or to guarantee the stability of the system. Navina, is it correct? Okay. What about you? Pavani. Okay, do you agree? Okay, if I ask a question, you can answer. What is the natural frequency? It is a frequency is coming from nature. No, no, it's providing the swing, okay? So when we reach in this point, we should be careful that this is the border of the stability. So when you make the simulation, you should consider that what is the natural frequency, and if we by mistake we don't go to the instability region. So any questions so far? Sir, yes. Yes. Yes, yes. Limitation is coming from omega n. So for example, if you reduce the value of omega n, inertia goes up. Okay? So, or increase the omega n, it goes down. So if we pass this limitation, I mean the omega n actually pass the limitation or borderline of the stability, then the system will be unstable. So by this, if we reduce too much the value of the j, then system will be unstable. If we pass too much for the omega n or inertia, system be again unstable. Omega n is the nature of the system. You cannot actually. It's not the constant value. No, it's not the constant value. It's the nature of the system. It's a natural frequency. Yeah. We can't change this value, but based on that, we should actually play with the parameters, with the voltage, frequency, lots of things. So, for example, we have the P max, and if we get back equation 11, omega in P max over to J omega S. Omega S constant, J constant. Okay, P max is EV, yeah, by X times 2 delta, and this delta is not the constant value, so it's changing. What? Yes, moment of inertia. You don't know? Okay, J, for example, is a constant value, 10. Omega is also second frequency, yeah? Is a constant, okay? So, P is equal to EV over, okay? Yeah, yeah, here, this one, okay? Yeah, this is one thing, but it makes the system unstable, because if you change the value of the V, it means that you are changing the value of the voltage over the load, and also E should be constant, otherwise your system generation is not constant. X is also the net, okay? So, but delta is not constant because the voltage changing over the, because the current are changing. So normally the omega n is not the constant value, because when you change the value of the load, then the voltage is impacts, and then also delta is changing, and also P is changing. So this type of and you are not expecting something extraordinary exploding in the grid. So some changes provide. This is why we call it sometimes a small signal. Yeah.
And this model will be able to provide or compensate inertia.
Yes.
Because in converter side we have switches and their capacity.
Mm-hmm.
So how we see that how much inertia capacity or
mean, your question is a little bit, if I say that, this one can be calculated by something, then it is not true. But we have the inertia constant. So it's coming based on the kinetic energy we can provide, okay? So W is 1 over 2 J omega 2. Omega is the constant, J is the kinetic energy. So what we have the kinetic energy. So J can be calculated from here, or we can say that much energy we need inject to the grid as a kinetic energy. So, any questions? Sorry. Any questions so far? Is it clear? Yes? Darshida, is it clear? Okay, very good. So, up to here is the model of the electromechanical model of the synchron generator, which is somehow included in the control loop of the power converter. Okay? So now we get back again to this system. We see that, J can be calculated by this, but you can consider that J cannot go very high, cannot go very low. And the reason is that it passed the border of actually this stability and system became unstable. So now this is the model that we have. In this model we have actually frequency synchronization to the grid, comparing a constant damping factor with the adaptive one. So it means that if in your model you have just the constant Kc and the system changes, it cannot adapt itself, so Kc cannot be a constant. But in previous chapter, we said that if we consider the Kc equal to a square root of 2 over 2, it means that we have the minimum overshoot. But here we see that no, the systems are different, because sometimes you are in the grid connected mode, then you go to the islanding mode and again get back to grid connected mode. So this should be able to damp the difference, because you have a converter, it connects to the load or connect to the grid. So the dynamic of the load and grid are different. So the swing value will be different. In fact, for the grid is much more bigger than the load. So in grid connected mode is more than islanding mode. So for this, if we have actually this for the grid connected mode, and then we have the adaptive one, we can see that we can damp the swing by this adaptive swing damping. Lenny, is it clear? Means yes or no? When you say like this, it means that this is yes, this is no. Some part is yes, some part is no. Okay? Okay, good. Now if I ask you to explain again, you can explain it, yeah? Yes or no? Okay. So if something is not clear, tell me. So then we consider the impacts of inertia. So we see that, we can calculate the value of the inertia that can be injected from converter to the grid, from this converter to the grid. And we see that if the inertia is less, we have the bigger actually frequency changes. And if we have inertia enough, you see that, when we have the low changes in the system, the drop in the frequency is not high. And this is also the reaction of the system. We see that, when this system happening, the voltage drop, we increase the value of the power and compensate it and reach the steady state operating condition faster. Okay? And for the load changes, if we see that, when we have the 10% load increment, the impacts of the inertia, and lack of inertia, and also impact of damping factor. We see that when we have the tune the damping factor better, we see that it's a much more better, but when it's not very good tune, at least this one is good also. It can be something like this when we have a bad tuning for the impact of, the damping factor. So we see that if we have the good damping factor and inertia, so by this we can have a quite good reaction during the dynamic changes in the power grid. Any questions so far? What? Drawback of this model? Which one? This all model? You mean that this model? Yeah? I think if you learn the strength of that and simulation, make the simulation, then you will see by yourself what is the drawback of this model, okay? So he's very smart guy to just jump this one, say, no, this is not good because it has this drawback, and that's, okay, so. Honestly, this type of technologies, we have the different types of the actually virtual, because virtual synchronous generator is not just based on this one. We have virtual impedance, virtual admittance, and we have the different types of the technology that we can consider. And basically, if you are going to compare, for example, if I compare this one with virtual impedance, said that, okay, this is better because it has the less disturbances. But then if you are going to compare this one with some other things, then probably the other one has the better or faster response to the changes. So it should be compared. But this is very actually very good model. It's one of the somehow top control technique that we can consider for the control of the converter. In ABB, they have a model that considers the, for example, reference voltage after the filter or before the filter, and then you see that sometimes it works for the they call it it was a power synchronization controller. It is synchronization power controller. That one is PSC. And then they later they develop it. It makes much more better. In the first version, it could not work for the stable grid because most of them working in a stable grid, but not for the weak grid. But it was the opposite because they considered the measurement of the voltage in some part that the weak grid impedance had the big impacts on the operation of the system. So for that one, then they modify the controller, and now both of them are working. But in this case, I'm not sure about the some. In the reference mentioned, it works very well in weak grid also, but I didn't test it. So, but for sure, any model that you are using as a benchmark have this possibility to be developed more. So, yeah. Any questions so far? Rakesh? You were absent yesterday, yeah? I miss you. You okay? Good. Yeah. Large disturbance? Yeah, of course. But I mean, what is the definition of large? Like a fault? Look, let me explain to you. What we are discussing here in the class is the benchmark, is the basic model of the system. So if later you are going to limit the current, then you should put the limiter in the control loop of the system. If you are going to fault rate at the fault rate capability, again you need to add the feature in the control loop. So basically it depends, but I can say that I can guarantee that this model, if you add fault through capability in the control loop, then it works very well. Yeah. So they are like a benchmark. So, any questions so far? Abe, you are the symbol of the inertia in our class. And your inertia is very high. Do you have something related to inertia for us? Any tip? Okay, no. Even he has no inertia to say something. Resisting. Okay? Good. So, now if we get back to this, we see that, you know, we have the model for the active power, but for the reactive power, you know that the inertia is coming to regulation of the frequency, and the frequency is related to active power. So by this assumption, we see that, you know, we can modelize this electromechanical part for the emulation of the inertia in the power grid. And then we have also this part, which if we get back the conventional method, it was the like IQ and I reference, and then PI controller, and goes that one to control the system. So up to here, you see that this is actually active and reactive power can be compensated, and somehow voltage and frequency also can be regulated. Okay. Now we are going to discuss about the contribution of the SPC to regulation of the frequency. Would you like to have 10-minute break? Or I don't know. Yeah? When did we start? More than half an hour ago, yeah? Do you want to have a break? Let's have a break up to what time? 11:30? 15? Okay, 15. Yeah, you're really tired actually. Stay. Yeah. Okay. So get back 11:15. In the class. Yeah, you're talking too much, trying to attract the people to, yeah. Yeah? So, now is the time, actually we see that, you know, the frequency can be handled from the active power side, and reactive power also can provide the voltage. So we have the voltage and frequency, and then VCO provide the voltage for the like a model of the voltage in the output of the synchron generator, and based on that we can react like a synchron generator for the grid. So now we are going to talk about the contribution of the SPC to regulation of the frequency. This frequency regulation is normally based on the provision of the active power, and we can control frequency based on the signal actually we get from the frequency, and then provide accordingly some deliver or absorb actually active power to the grid, and then regulate it in the required boundary we have. So we have a control, we call it drop control, and the idea is that actually we keep the frequency between the dead boundaries. So it means that, for example, for here 0.4%, it means that we can, if we consider the reference 50 hertz. So we can have the fluctuation 0.4% up or down. Okay, so 0.4% means that 0.4 times 250. Okay, so by this value we can actually stay in the steady state. I mean, in the right operating condition. But if the frequency drop more, we see that the frequency actually changing more. Then the value of the active and non-active power injected to the grid or probably absorbed from the grid change. So for example, here we see that the frequency past this 0.4%. So when it passed, it means that frequency go more. So now it's 50 hertz. It goes to more than 51, 52, 53 like this one, okay? So it means that we need to reduce the active power. So if we increase like this one, in fact, the frequency increase more. And then here also we see that the frequency is 50, but we see that the frequency is dropping. It's the minus side, okay? So it goes toward the 29 hertz. So we see that when we pass this dead band, we need to inject more power. So here was the constant power we inject, but now we see that because the frequency is dropping, then we increase the value of the active power injected to the grid by use of the virtual synchronous generator. Is it clear enough? Okay. So this is the droop controller that we use for the regulation of the active power. So for this, we have actually one loop. We consider the frequency, reference frequency. What is the value of the reference frequency? Abe? What is the reference frequency? What is the value for omega star? What? No, what is the value? 120, I don't know. Frequency. 50. Frequency. Yes, 50 hertz. Yeah. Okay. So we need to have the 50 hertz. 2 pi times 250, 340. Okay, 14. Okay. So, but the frequency that we have in the grid is omega. So it can be 50, it can be 50 point something, 51, 52, 49, something like this. So we measured the frequency of the grid, and we also have the reference. We compare together. So if delta omega is in this operating condition, so fluctuation is in the dead band here, we cannot do anything, is completely fine. But if it goes the different direction, we need to actually calculate the value. We call it this drop frequency coefficient. And based on that, we change the value of the active power that we need. So for example, if frequency drop, so assuming that we inject in 10 kilowatt, and then frequency drop to 49, then it means that our frequency are dropping, then coefficients provide the actually value to the P and increase the value. So it said that, in a state of 10, now you should go 11 because the frequency are dropping. Okay? So by this assumption, we can provide the P reference based on the situation of the frequency, and we can somehow regulate the frequency of the grid. So, is it clear? Yes or no? Yes or no? No. Okay, good. No is better than fake yes. So assuming that we have a grid, this is the grid is 400 volt and 50 hertz. Okay? Navina? Okay. Then you are going to inject power from the renewable energy to the grid for regulation. Okay? So, and 10 kilowatt is connected to the grid. Okay? So it means that, grid inject 10 kilowatt power, provide the 10 kilowatt power to supply it. Okay? Then the load increased. At the first stage, it increased 1 kilowatt, again 2 kilowatts more, and again 3 kilowatts more, and 1 kilowatt again. Okay? So the load increasing. So when the load increasing, frequency dropping. Okay? So frequency was 20. When it was actually 1 kilowatt more, it became 49.9, then 2 kilowatts, so 49.75, and then 3 kilowatt, 49.60, and you see that the voltage is dropping. So then, how do we understand that now we should increase the active power from here? It means that we see the frequency. So what is our frequency is 50 hertz minus this frequency happening or changing in the grid frequency. So we have the delta, yeah? So if delta change more than 0.4%, okay, it means that now our frequency is in a wrong place. We are not allowed to have more changes than this value. So this gives the information delta F is equal to K delta P, or dF delta P. Okay? So it means that it gives some information to the converter. If, for example, now we inject 10 kilowatt, it should increase. Why? Because the frequency dropping. So by this, we increase the value. So in this stage, we see that it can be 11 or 13 or 16. So we increase the power injected to the grid. Then we fix the frequency again to 50. Was it clear? 100%? Does anybody can say, okay, probably is not 99.9%? You are not allowed to say 99.9%. You should be 100% sure that you understood the concept. Arya? 99.9 or 100? Last part, okay? So do you agree that delta V, delta P, active power changes, can change the frequency? Do you agree? Assuming that I'm a frequency, okay? Then I have a backpack. You have actually some load in my backpack, and when you increase the load, my speed drop, okay? So frequency drop when load increase, okay? So when we have the increment in the load, in fact the frequency drop. And when the frequency drop, we notice by measurement. So we measure the frequency of the grid and compare with the frequency of the steady state, like a 50 hertz. So if it passed the dead band, it means that our system frequency is not stable. So by this, we update the reference for the converter, and converter inject in a state of 10, we increase 12, 13. Then we return back the frequency again to the deadband. Any 99.9%? Other? No? Okay. No? Good. So now we look at here. We see that, you know, when the frequency is in 50 hertz, so nothing happening, we have the actually power and we have the stable frequency. But when the frequency is changing, we reach in the dead band, and we see that the active power fluctuating a little bit, and this is because of the inertia. It is not because of the power changes, because inertia can damp the changes. So you see that a little bit changing happening here, but it is not sensible. If it doesn't change, still you are in the right position. But when we pass this dead band and the regulation change, and when frequency goes up, we see that the active power goes down. So by this, we balance the frequency by the reducing the active power. Okay? So for example, if the load is less, then we reduce the value of the active power, update our reference value. By this, from 10 to 8, again we get back the right frequency. Okay. Now we have also this regulation for the voltage. So in fact, we consider the voltage in the dead band. So we said that, okay, if we have 2% voltage change, turbulence, it's fine, fluctuation. Okay. So if we have actually see that, you know, this is the reactive and this is the voltage. So by 2%, if our voltage is 100, it means that we can go to 102 or 98. So if we fluctuate between the 98 to 102, it is still okay. But when we pass this part, so in fact, when we have the drop in the voltage, the voltage past the 2% increment, in fact, we should reduce the value of the reactive power. So the reactive power goes from the, I don't know, something to less. And if we have the voltage drop less than 2%, we see that we need to increase the value of the reactive power to return back the value of the voltage to this value, between 98 to 102. Is it clear also? Pavoni? Pavoni? No? Is yes or no? No? Okay. Okay.
How do you deciding that group constant chemical?
This is calculation. Reactive, and you see the system and know what is the value of the impact. So because we have the voltage times 2 something is equal to Q. Yeah, yeah. I mean, if you get back to, for example, that discussion we had with the Park transformation, P was equal to VD times to ID, and Q was equal to minus VD times to IQ. So when we have the VD, then we can also consider IQ. So play with this value. So now VD is a constant, should be constant. Okay. So then we have the Q. So by changing the Q, you can consider that how much actually VD can be somehow changed. So now here, so assuming that this time this converter is injecting 10 kiloampere reactive to the load, okay? when the reactive load increase, the voltage drop. When active power increase, frequency drop. Okay? So when we increase the reactive power more and more, in fact, the voltage over the load reduce. So by this, if the voltage is between 102 and 98 up to 102, it means that 2%. So still that much fluctuation is okay. It depended to the grid code. Some countries said 2%, some 1%, some 0.5%, but doesn't matter. This is an example. So when we are in this operating mode, still this 10 kilovolt ampere reactive is enough to keep the voltage in this operating condition. But when we increase, for example, 2 times or several times more the value of the reactive, then voltage goes to, for example, 95. Drop 5% instead of 2%. So by this, we need to update the reference from 10 to 15, or from what the value that we need to compensate and return it back to this operating condition. So by this, we have actually one troop controller here. It measures the value of the voltage and compare the voltage reference we have. And after that, pass this deadband, and if it exceed the value between the deadband, then this D provide the required or update the value of the Q to compensate the voltage that we need for the stability of the grid. So by this, if the reactive load increase, our converter increases more reactive to compensate the voltage drop. And if decrease, we can also update the decrease, the reference value of the reactive power and compensate the actually voltage fluctuation in the grid. Was it clear, Abe? Good. Yeah, okay. So this is the nature of troop control for the SPC. So now we get back again to just an example. So let me get back here. We see that if in a state of providing just this control loop, we get back to this model, and this model, in fact, our system is working like a virtual synchron generator. What is the virtual synchron generator, Lenny? Lenny, look at me. What is the virtual synchron generator? When I was in the elementary school, we had actually one friend, still I remember him clear. When the teacher asked him why you didn't provide the homework, he did like this. Now you remind me that guy. Is it Lenny? Okay, tell me. So what is the virtual synchron? What is the benefit of the virtual synchron generator? Darshita, tell her. She look at her face like this. Means that you don't know really. Okay. So why we need this one? Look, by this we can provide active and reactive power for the grid, okay? But we cannot provide something like inertia and provide the stability of the grid. And the problem of the first model is that when we increase this type of controller or this type of control-based generator, in fact, we provide more problem for the grid, and grid became more unstable. So for this case, we developed the control loop based on the machine, which provide the inertia beside the injection of active and reactive power. And the good part of this machine is that it can also regulate the voltage and frequency of the system beside the provision of the active and reactive power and inertia for the grid. So, I forgot to say something. If I remember, return back. So if we get back to here, we see that the voltage is, for example, 2%, up to 2%, nothing happening in the reactive power. If you get back to here, you see that one small thing is happening here. But why it is 100% nothing here? Does anybody knows why? In active power, when even we were in this dead band, we see that the frequency is changing, but it still is in the 0.4% band. So it is still, it is not, drop is not active, drop loop. But we see that it's not completely like this. It has a little bit ramped down. And this is because of the inertia. Because inertia also somehow changed that one. But inertia doesn't have any responsibility for the reactive power. So when the voltage dropping, still this is not active, and we have completely what we have here is here. But when we have actually passed the 2% voltage drop, we see that the reactive power injects. So reactive power increase, and it provides somehow supportive functionality to regulate the value of the voltage over the grid. So now this is an example of the system that you know how we can actually provide the inject from the three-phase system to single phase. So we see that we have the voltage sag here, and then we provide the increment in the value of the current, which is basically provide the active and reactive power for the grid to compensate here is the voltage, so compensate the more reactive power to compensate the voltage drop in the power grid. So now again we get back in the beginning of what we discussed. If we get back the beginning of the chapter, we said that what is happening here is that inertia provides the resistance against changes. So changes can be someone is sitting in a chair, or probably hamster running here, or blowing in pinwheel. So when I stop anything, you see that it still have this possibility to continue. But as long as actually this inertia is less, it returns back or changes faster. So in the power grid, we also have this type of problems when the fault happening, and then we need the inertia to keep the stability of the grid before, for example, governor detects the changes in the frequency, and after that we can actually increase the value of the speed and compensate or balance the generation and consumption. So this time that this compensation happening, inertia keep the system unstable. So we have this transient time, which inertia keep it stable. So, and again, do we need to be panic when we have more renewable energy in the system? We say no. Why? Because we have this type of technology which can provide the inertia for the grid even by using the power electronic system. So we call this type of power electronic generator, we say virtual synchron generator. And the reason is that we use the power electronic, but we emulate behavior of the synchron generator in the operation of the system. And this converter behave like a synchron generator. So this is not synchron generator, it behaves, so it's like a virtual synchron generator. So in the synchron generator, this is the most important equation, swing equation, which provide based on the frequency fluctuation which is under active and active power transition, and also limited by inertia. So we also talk about the inertia constant, which provide the value of the inertia over the rated apparent power of the system. So as much as this value h is more, in fact the system has more inertia. And just the example is that, you know, when you have here a machine which the inertia actually constant is 4.93, it means that when we stop the power, it can continue up to 4.93 seconds to keep the system still stable. So you see H 493 means that generator can sustain its kinetic energy for about 493 seconds at full load before depleting. So if something happened, you still can continue for that time. So it means that governor have system have 4.93 times second to return back to the stable operating condition. So this is the model of the machine that we had. We have the generation, consumption, grid, and we have active power and reactive power injected to the grid. And then the angle data is the angle between these two voltage. And we also discussed that if we are going to consider emulate the behavior of the synchronous generator in the control loop, we need to modelize the electromechanical model of the synchronous generator in the control loop of the converter. And we also considered that this equation, we discussed that how we jump from input power and create the output power. So by this, we can replace actually electric power and then we provide the natural frequency, which somehow create the marginal stability for our system. So we should be careful about that one. And then we said that, I mean, this type of technology based on the conventional power generation or synchronous generator, they have some benefit. They can provide the inertia of the system and increase the stability of the system. But the weakness is that the damping factor is not working very well because it has several limitations due to the mechanical and electrical limitations. So for this case, we develop a PLC here that measure or calculate the value of the frequency changes based on the changes in the active power in the machine. So by this, we can actually calculate the angle and active power injected from the converter to the grid. So this is the model electromechanical model of the machine, which is embedded in the control loop of the converter. So up to here was somehow some equations. We see that we can provide the new damping factor and inertia to support the grid inertia and provide the faster damping factor to changes. And here is the result when we have the actually compare the different operating condition with the constant damping factor or variable adaptive damping factor, and with the inertia or without inertia, and other changes also. So then another part of this technology was the calculation of the reactive power for the regulation of the voltage. So for this technology, we use the drop controller. We have the PF and also QV. So based on the change of the active and reactive power, we can regulate the voltage and frequency in the system. So by this assumption, everything goes well, and we create the drop control loop in control of the converter generator embedded in the control loop of the converter. So later, just in a state of having this one in chapter 1, now we can consider this one in chapter actually studied in chapter 5, to provide the supportive functionality for the grid. And what is happening, it means that if later in India, when you are going to increase the share of the renewable energy more than 30%, 50%, 70%, or 90%, we don't have problem regarding lack of enough inertia to keep the or guarantee the stability of the grid. So this is chapter 5, and Udaya, you want to continue your part? Yeah, because you mentioned that you have also one part to continue, because we have one chapter. So today we continue with lab. We have also an exam, and then tomorrow we close the chapter 6 with the predictive control analysis, and then what I promise is finished tomorrow. And if we need more, we can also get back to this 6th chapter or lab because I have no idea about the Thursday. But yeah, but Thursday you mentioned you have the ceremony and this type of things. Certificate distribution. You are going to give the certificate to all? Okay. Okay, good. Yeah, so. Okay, yeah. Mm-hmm.
Inertia part, maybe the ground is sufficiently supported.
Mm-hmm.
Any other issue?
Yeah. Yeah, okay. One aspect is the inertia, okay? It means that when the inertia is not enough, in fact, you have the problem for the frequency changes. But then the other is that this type of distributed generated system, they provide also harmonic for the grid, and also they reduce the impedance increase the impedance of the grid. So if you are going to compare conventional grid and future grid, for sure the future grid are more weaker in comparison with, and dynamic operation of this type of system are much more faster. So they have a problem with the dynamic stability of the system. This is one thing, and then we have also some loads based on the power electronic devices. For example, we have electric vehicles. So electric vehicles are initially charged by the charging station, which converting this sinusoidal to the DC. So they are also power electronic based loads, which provide also lots of harmony for the grid. And then they have also new technology based on the fast charging devices. So it provides a big spike over the grid. So these type of technologies, these type of problems will be appeared in future grid. But the good news is that if we increase the inertia of the grid, in fact, it means that, although we have too much problem, but we have also enough energy to damp this type of problems. As long as generation and consumption are balanced, and the system has enough inertia, then we can say that our system is somehow secure. We cannot guarantee it, but it's somehow secure system. Yeah. Any other question? If you want, I can, but yeah. It's I think that because because if I start today, then tomorrow also I should return back to repeat again. The chapter is completely Okay. Afternoon is lab. Okay. How was your simulation class? Very bad, yeah?